Hi, Terry here. My software life has been a case of love or hate at first sight. Love at first sight definitely applied to Unix. I just fell heads over tails for Unix the first time I saw it. And another case of love at first sight is Xschem, the subject of this podcast. My first test of Xschem is the LM324 crossover distortion schematic and simulation around the 7-minute mark.
So if you want to design a manufacturable silicon microchip today, you'd probably think you need to, sign some massive non-disclosure agreement.
Oh, absolutely. And pay a foundry millions of dollars just for the software licenses alone.
Right. It's this whole industry built behind these towering financial and legal walls. But what if the key to bypassing that massive barrier isn't some sleek AI-driven Silicon Valley startup?
Right.
What if it's actually an aggressively utilitarian, keyboard-only piece of software from 1998?
I mean, it sounds completely counterintuitive, right? You would expect the software used to design the microscopic billion transistor cities inside our smartphones to be just as polished and modern as the phones themselves.
You really would.
But the tool we're looking at today actively rejects that aesthetic. It's frankly kind of shocking to look at first.
Yeah, it really is. And so, welcome to the Deep Dive. Our mission today is to explore how anyone, and I mean anyone, from an absolute beginner writing their first code to a seasoned hardware engineer, can simulate and design real, physical silicon microchips for free.
Right, from your own computer.
Exactly. We're unpacking a stack of research on a tool called Xschem. And just to clear up any naming confusion early on for you guys listening, while it sounds similar to another tool called Xschem, they are completely unrelated projects.
Yeah, totally different things.
Xschem is a dedicated open-source schematic capture program, and it is built relentlessly for integrated circuit design.
And to understand why Xschem is so incredibly powerful, you really have to look at the 28 years of evolution behind it.
28 years! That's a lifetime in software.
It really is. It was created back in 1998 by a developer named Stefan Schippers. And the underlying architecture is just fascinating. It's this hybrid engine.
What do you mean by hybrid?
Well, it's written in about 66% Sine, which totals around 70,000 lines of code. But then it also uses TCL for the user interface scripting, Scheme for an embedded interpreter, and awk for utility scripts.
Okay, wait. That sounds like a complete Frankenstein mix of 90s programming languages.
It really does sound like that on paper.
Why build a visual design tool with such a fragmented stack? I mean, isn't that just asking for trouble?
You'd think so, but it's because of the staggering benchmark Schippers was aiming for. He wasn't building a tool to just draw a cute little resistor network for a breadboard project,
Right.
He was targeting very large-scale integration, or VLSI. We're talking about custom application-specific integrated circuits with 1 million transistors spread across 10 nested levels of design hierarchy.
Oh, wow. 1 million transistors.
Yeah. And if you try to render 1 million nodes using a high-level modern language with heavy overhead, your computer will just grind to an absolute halt.
Oh, so it's a performance thing.
Exactly. The C code handles the heavy lifting, right? The raw memory management and the lightning-fast rendering. Then the TCL layer sits on top of that, and it provides this lightweight scripting environment.
So engineers can write custom macros and automate the interface.
Spot on. They can do all that without having to recompile the Core C engine every single time they want to tweak a button.
So it's basically a dragster, just stripped down to the frame for pure speed.
That's a great analogy, actually.
Which totally explains the visual shock you get when you actually boot the software up. I mean, opening Xschem feels like logging into a terminal window from a 90s hacker movie.
It really does.
There is no dark mode. There are no smooth animated panels. In a world of intuitive drag-and-drop apps, isn't a retro interface just, developer stubbornness?
A lot of people think that at first. But the creator explicitly rejected modern graphical user interface trends. And it isn't stubbornness. It's a calculation based on extreme physical scale.
Okay, how so?
Think about the environment you're working in. If you have a schematic loaded with 100,000 delicate wires, components, and microscopic logic gates relying on your mouse to click and drag, that's a catastrophic liability.
Because of the precision required, like one accidental flinch of the wrist and you pull a wire you didn't mean to.
That is not an exaggeration at all. A millimeter slip of the mouse in a standard drag-and-drop interface triggers the software to instantly grab whatever's under the cursor and move it.
Oh, I see.
You might drag a power rail into a ground line without even noticing, hit save, and suddenly you've ruined a complex silicon layout that took months to architect.
Yikes. That's terrifying.
Right. Furthermore, dynamically recalculating bounding boxes and connectivity for 100,000 items just because you lazily dragged your mouse across the screen. It's incredibly computationally expensive.
Which forces the question, if a slick modern drag-and-drop interface is actually dangerous at this scale, how on earth do you interact with it?
By demanding explicit intention through strict keyboard bindings. Xschem fundamentally alters your workflow. You do not just wildly click around the canvas.
So what do you do?
If you want to move a component, you hover, you press the M key on your keyboard to explicitly state your intention to move, and only then do you interact.
Oh, okay. M for move.
Exactly. If you want to copy a block of logic, you press C.
It makes the user slow down, basically. You have to declare your action to the software before it even allows you to touch the delicate machinery.
That's exactly it. And this extends to how you navigate the massive scale of the designs, too. You mentioned those 10 levels of nested hierarchy earlier.
Yeah.
To keep the screen manageable, a complex block-like an arithmetic logic unit is just represented as a simple square box.
Right. Otherwise, you couldn't see anything.
But if you want to see the transistors inside that box, you select it and press E to descend into the subcircuit.
E to descend. Got it.
And when you're done inspecting the micro details, you press Control E to pop back up to the macro view.
Now, the research notes that version 3.4.5 did eventually introduce an optional intuitive click and drag mode, right?
Right.
For users who just can't let go of their modern habits.
It did, yeah. But the purists, the people building the really massive chips, they stick exclusively to the keyboard language.
They just memorize M, C, E, and Control E.
Exactly. Because once that muscle memory sets in, you completely stop fighting the GUI. You just start thinking entirely about the physics of the circuit.
Well, that's actually the perfect transition to the practical side. How does a total beginner actually put this keyboard language to use and, simulate their very first circuit?
So the sources outline this brilliant real-world example. There's a test circuit designed to demonstrate a phenomenon called crossover distortion using an LM324 op-amp.
And just to define crossover distortion quickly for you listening, it's this ugly glitch in analog audio amplifiers where the output signal stutters or flattens out right as the voltage crosses zero.
Exactly.
It happens in that microscopic dead zone when the positive transistor turns off and the negative transistor turns on.
It's a classic problem. Every analog designer has to learn to spot it. So to build this simulation in Xschem, the setup is incredibly logical.
Walk me through it.
You use your keyboard shortcuts to place the LM324 op-amp symbol on the canvas. Then you need to power it, so you drop in two DC voltage sources, a plus 10-volt supply and a minus 10-volt supply.
Okay, makes sense.
Then you add an input signal, which in this case is a piecewise linear voltage source to sweep the input up and down. And finally, you attach an RC load, just a simple resistor and capacitor network, to the output pin.
But at this point, we just have a static drawing, right? Just shapes on a screen.
Yeah.
How do we tell the software what physical parameters these shapes actually represent?
That's done through Xschem's parametric engine, which is fully built to maximize design reuse. Instead of going into every single transistor and hard-coding its physical width and length.
Which would take forever.
Exactly. Instead, you can define parameters at the top level of the design block. It's essentially like passing arguments to a function in a programming language.
Oh, that's clever.
You define the variable once at the top, and Xschem dynamically passes that value down through all the nested levels of subcircuits, adjusting the physics of the components on the fly.
So if I spend a week designing this complex analog amplifier block, and then I need to reuse it later in the chip, but with, say, a slightly higher current capacity, I don't have to redraw anything.
Not a single line.
I just tweak the parameter variable at the top, and the new physics propagate down through the entire system.
That is the beauty of it. And once your schematic is parameterized and all wired up, getting it ready for simulation is remarkably elegant. You simply press the netlist button.
I want to pause on that for a second because the process behind that button is fascinating. It doesn't just export a static image of what you drew.
No, not at all.
Xschem recursively traverses your entire design hierarchy, flattens all those parameters you just set, and generates a fully self-contained SPICE netlist.
And a SPICE netlist is basically the mathematical truth of your circuit. It's this plain text file that lists every single electrical node and exactly what is connected to it.
Right.
But Xschem goes a step further. It automatically injects the .mod files, which contain the complex physics equations for things like the LM324 transistors.
Oh, wow.
And it automatically includes the transient analysis control statements. It hands the simulation engine a completely execution-ready file.
Okay, so the math engine crunches all the numbers in the background, but looking at a raw text file of millions of voltage calculations is pretty much useless to a human.
Utterly useless, yeah.
How does a beginner actually see that crossover distortion glitch we talked about?
So this is where Xschem turns its utilitarian interface into a highly data-rich canvas. Rather than forcing you to open a separate plotting application and, juggle multiple windows,
Which is annoying.
super annoying.
Yeah.
Instead, you can embed a live waveform graph directly into the schematic file itself.
Right next to the wires you just drew.
Exactly. For the LM324 test, you embed a graph showing the results of a 500 microsecond transient simulation. The graph is live, it's zoomable, and cursor measurable.
That's awesome.
You can zoom right in on the 0-volt crossing on the y-axis and clearly see the flat spot. You can see the exact moment the output signal stalls before the negative transistor catches it.
The embedded graph is cool, but the feature that really feels like a superpower for a beginner is the live annotation.
Oh, the live voltages, yes.
Yeah. Xschem actually parses the raw binary output file from the simulation engine, and it overlays the resulting DC voltages and drain currents directly onto the visual nodes of the schematic in real time.
It literally maps the abstract mathematical data back onto the visual geometry you drew.
It's like turning on X-ray vision for your circuit. When you move your measurement cursor along the timeline of that embedded graph, the actual voltage numbers floating above the wires on your drawing update instantly.
To match that exact nanosecond in time.
Yeah, you literally watch the electrical pressure rise and fall through your schematic.
It fundamentally changes the learning curve.
Yeah.
You're directly connecting the schematic abstraction to the physical reality of electricity.
Right.
But, simulating a single isolated op-amp is a pretty contained experiment. The real magic happens when you move from simulating a textbook circuit to designing manufacturable silicon.
So how does a tool from 1998 become the engine for designing actual chips in the 2020s?
Well, that brings us to a massive paradigm shift in the semiconductor industry. In 2020, Google partnered with a semiconductor foundry called SkyWater Technology.
Okay.
Together, they released a fully open-source 130-nanometer process design kit, or PDK.
And to put that in perspective for you listening, a PDK is basically the sacred rulebook of a silicon foundry, right?
That is exactly what it is. It contains the exact geometric design rules, the parasitic capacitances of the metal layers, and the precise physics models of the silicon wafers they manufacture.
And historically, foundry PDKs are guarded like state secrets. I mean, you couldn't even look at one without signing a mountain of legal documents and paying extortionate software licensing fees.
The SkyWater 130 release completely shattered that wall. Suddenly, the precise physical parameters required to print a 130-nanometer chip were available to anyone with an internet connection.
Which is huge.
And Xschem, with its ability to handle millions of transistors without crashing, was perfectly positioned to become the drawing board for this new open-source silicon revolution.
And setting up a professional-grade, foundry-ready toolchain today is shockingly simple. You don't need dedicated servers, you just need a standard Linux machine.
Yeah, the sources detail this incredibly simple 4-part toolkit you can install straight from a standard package manager.
So, step 1. You install Xschem itself, which on the system in our research was running version 3.4.8 release candidate.
Right, so that's your visual canvas.
But out of the box, Xschem doesn't know anything about SkyWater's silicon, so step 2 is installing a package called OpenCrease.
Right. Think of OpenCrease as the translation layer. It acts as the bridge, providing Xschem with all the specific symbols and parameterized models for the Sky 130 library.
Got it.
It loads the exact N-channel and P-channel transistors, the standard digital logic cells, and the heavy-duty input-output pads required to interface the microscopic chip with the outside world.
Okay, so step 3 is the math engine. You install Ingspice, and when you place special code-shown symbols in a cap, to inject Spicia commands directly into your drawing, Xspice is the program that seamlessly fires up in a Sturm window to calculate the physics when you hit simulate.
Exactly. And step 4 completes the physical reality. You install a layout tool called Magic.
Magic.
Yeah, Magic takes the verified netlist from Xschem and turns it into the actual geometric polygons that will be etched onto the glass photolithography masks at the foundry.
It is wild that an entire silicon toolchain boils down to 4 free Linux packages.
That's amazing.
I mean, if you're a beginner, you boot up Xschem with the Sky 130 PDK loaded, and you are immediately presented with a welcome page.
Yep.
It has fully wired, ready-to-simulate example circuits on the left, and a library of every silicon device you can manufacture on the right.
You just place your transistors, wire them up using your strict keyboard shortcuts.
Right, your MCE, Control E.
Exactly. You inject a transient analysis command, and you can literally be simulating genuine silicon and physics in under an hour.
It completely democratizes hardware design.
It really does. Yeah. But we should emphasize that Xschem is not just a set of training wheels for beginners. It is actively used to tape out complex enterprise-level silicon.
Which brings up the challenge of scaling. Because modern chips are not just simple analog amplifiers.
No, they're massive.
They're a messy, highly complex collision of analog components and massive digital microprocessors sitting on the exact same piece of silicon.
A total mixed-signal nightmare.
Exactly. So how does a single schematic tool simulate the continuous sweeping voltages of an analog op-amp alongside the billions of discrete, snapping digital clock cycles of a microprocessor?
Through advanced co-simulation capabilities,
Right.
Xschem doesn't force you to design the analog and digital halves in complete isolation.
Well, that's smart.
Within a single schematic file, you can link the analog blocks to be mathematically simulated by spicing in continuous time, while simultaneously passing the digital logic blocks to a Verilog simulator like Icarus or Verilator to handle the discrete digital events.
And it even has a built-in digital logic simulator right in the schematic, doesn't it? Like, you don't always need a heavy external Verilog tool just to verify basic digital routing.
Correct. You can watch digital logic states propagate live on the screen. The nets literally toggle between a 0, a 1, an X for an unknown state, or a G for a high-impedance disconnected state, all visually overlaid right on the wires.
That's incredibly helpful. But as these mixed signal designs scale up to thousands of commits from dozens of engineers, you run into the ultimate professional bottleneck.
Automation.
Yes, automation. This is where we get into the most surprising feature of Xschem. It has a built-in TCP remote interface.
Which is wild for a drawing tool.
Right, meaning you can open a network socket and control the software via Python or TCL scripts. It has a fully headless mode.
Fully headless mode for a visual drawing tool.
Wait, let's unpack that. If there is no graphical user interface rendering the lines and boxes on a monitor, what is the software actually doing? That feels completely contradictory.
I know, but think about a modern continuous integration, or CI, pipeline in software engineering.
Right.
In a professional chip design firm, you might have 50 engineers pushing updates to a central Git repository multiple times a day.
Right, constantly committing code.
You cannot have a human being sitting at a desk, manually opening every single updated schematic, clicking the netlist button, and visually checking for errors. It would take forever.
Ah, I see the mechanism now. The CI server uses that TCP socket to wake up Xschem in the background in headless mode.
Yes.
The server script tells Xschem to load the latest file, recursively traverse the hierarchy, generate the spicy netlist, pass it to ingSpice, and grep the output file for timing violations or short circuits.
You got it.
It programmatically approves or rejects the engineer's work without ever rendering a single pixel to a screen.
Precisely. It treats hardware design with the exact same automated rigor as modern software engineering. And this automation is vastly empowered by one specific architectural decision: Xschem's file format.
The plain text files. I was wondering why the sources emphasize this so heavily.
It's crucial.
Whether you are saving a schematic with a Dotch extension or a reusable symbol with a .sim extension, the files are just elegantly simple, human-readable text.
Let's contrast this with proprietary commercial tools for a second. If you use a massive corporate software suite, the schematic file is usually an encrypted proprietary binary blob.
Right.
So if a junior engineer accidentally drags a critical wire out of place
Right.
and they commit that change to a version control system like Git, the system just says binary file changed.
You have absolutely no idea what they broke. It's just a black box.
Exactly. But with Xschem, every line of the file starts with a single character denoting what it is: a V for version, a C for component, and N for net.
So if that same junior engineer moves a wire, the Git diff shows you exactly which line of text changed. You literally see the N line update its geometric coordinates from, say, a y-axis of 100 to 120.
It is perfectly differently. It allows massive teams of hardware engineers to merge complex geometric layouts using standard software version control without corrupting the files.
That is the real aha moment for me. The retro aesthetic, the keyboard bindings, forcing intention, the plain text file format. None of this is an accident of a 1998 codebase.
Not at all.
It is a laser-focused philosophy on system stability, automated integration, and treating hardware design as code.
It is the product of knowing exactly what causes catastrophic failure in a billion transistor project and engineering a tool that systematically removes those failure points.
So, to synthesize this journey, Xschem proves that the barrier to entry for real manufacturable silicon design is no longer a six-figure commercial license.
Thankfully.
With 28 years of relentless optimization, strict keyboard precision, and deep integration with open-source foundries through the Sky 130 PDK, it really is the ultimate engine for the open silicon movement.
And its ethos continues to align with that movement today. Xschem is actively in the process of migrating its repository away from corporate-owned platforms like GitHub and moving over to Codeberg.
Oh, Codeberg, right.
Yeah, Codeberg is a European, nonprofit, fully open-source platform, which perfectly mirrors the philosophical foundation of open-source hardware.
It's an ecosystem that demands transparency at every level of the technological stack.
Absolutely. But, there's a final vital piece of this ecosystem that extends beyond the silicon itself. We have spent this entire discussion focused on the microscopic world, the layout of transistors inside the tiny black square of a microchip.
Right, the stuff you can't see.
But Xschem is quietly building a bridge to the macroscopic world as well.
Wait, you mean the physical circuit boards?
Yes. Xschem is a core component of an ecosystem known as Correlata. Through this initiative, it's actively integrating with macroscopic layout tools like PCB Estrin.
Oh, wow.
And they achieve this using a shared standardized netlist format called TDAX.
Which means the flow of engineering truth doesn't just stop at the edge of the silicon die.
Exactly. The future of open-source hardware relies on an unbroken chain of transparent data.
Right.
The exact same plaintext data structure that defines the width of a microscopic transistor inside Xschem flows seamlessly out through the TDAX netlist to define the physical, macroscopic copper traces on the printed circuit board you hold in your hands.
The invisible metropolis perfectly synchronized with the highways of the motherboard. It is just a stunning feat of engineering.
It really is.
So the next time you pick up a piece of impossibly sleek modern technology, remember that the foundation of the open hardware running it wasn't built with flashy graphics or drag-and-drop ease. It was built with plain text, extreme precision, and the explicit intention of a keyboard stroke. Thank you for joining us on this deep dive. Go install Xschem, explore the Sky 130 PDK, and experience the physics of silicon for yourself. We will catch you next time.
This concludes the end of the podcast. I hope you've enjoyed it, and as always, if you have any constructive comments, pop them below the video in the comment section, and I'll see you next time.